our example. So we're going to take this mapping, and we want to find the image of L of C, which is the imaginary line. So it's this thing. It's the set of C plus I, y belong to R. So it's the imaginary line that goes for the real number C. Right? So this is 0. I'm going to need a bigger picture than this, but okay. This is C. So it's the image of this thing. So solution. All right, so let's start to try and figure this out. Well, let's look at our initial mapping. Do you think that the image of this line will be either a line or a circle? What do you think? Well, that's a stupid question. Of course, it's a line or a circle. Which is it, a line or a circle? Mm-hmm. Yeah, exactly right. So if C is not equal to 1, then f of L of C is a circle, otherwise a line. Okay, so let's try and figure out elementary properties of this. So I should have put this on the left-hand side, but okay. This is where we're starting from, and we're mapping it with mapping, we called it F, right? And let's consider the case when it's not equal to 1, because this is the harder case to begin with. So take C not equal to 1. It's got to be a circle, right? So when you're doing this homework problems, a really good idea is to take colored pens and to draw stuff in the domain and then draw stuff in the image that you know it's being sent to. Okay, so we know that this thing is going to be sent to some sort of a circle, and that's all we know at the moment. But we want to begin by exploiting the fact we have angle preservation. So we see that this line is perpendicular to the real line. So let's think about what happens to the real line. See if we can understand that. So if we look at this thing applied to the real line, well, there's a couple things we can do. So want to find f for the real line, because that's going to be easier than our general line L of C, right? And what do we notice? Well, we notice that f of 1 is infinity, as already pointed out. F of 0 is just going to be -1, right? And what else? And f of infinity is just equal to 1. So 1, 0, and infinity all belong to the real line, and these are all points on the real line, so the real line must be sent to the real line. Yeah? Yeah? We know the real line will be a line because it does go through 1 itself, right? And the line that we have goes through infinity, -1 and 1. In fact, just knowing -1 and 1 would be enough. So we know that the real line is mapped to the real line. So let's make this thing blue. I don't know how well you can see that. So let's put little circles here. And we know that this thing is being mapped to this thing. like this. Yeah? Cool. All right. Then what else do we know? Well, let's think about the intersection points between this line L of C and the real line. Well, they intersect at C, right? Yeah. And they also intersect at infinity. Yeah, they also intersect at infinity. So we have that the image of L of C is some sort of circle that intersects this thing in a perpendicular way at 2 points, right? One of which will be the image of infinity, and one of which will be the image of C. Yeah. So f of L of C intersects the real line at f of C and f of infinity. And what is f of C? Well, it's some complicated expression. Let's keep it like this. And what is f of infinity? F of infinity is just 1. Right? And we also know that f of C is f of C is a real number, but we know that the circle has to have its center on the real line, because if it didn't, then there's no way that the angles which it crosses can be perpendicular. Yeah. So it has to be something that has its center on the real line, and we know that the circle is intersecting this line at these 2 points. So f of C is just some real number. So it's C plus 1, C minus 1, whatever that is. So it depends on whether or not C is bigger or less than 1, right? But just to put something somewhere, let's just put this thing here. Yeah, let's put this thing here. So this is 0. So let's say this is f of C, and this here is 1. And it could be that f of C is on the other side of 1. We don't know yet. We're going to figure that out. But they're both on the real line. And what the circle has to do is it has to intersect these two things, so the circle has to go like this. The circle has to go like this. Yeah, so this thing has to be f of L of C. Okay, and that gives us a lot of information. I mean, so we know explicitly what this point f of C is, right? So we could find the diameter of this circle and therefore its radius, yeah? Just explicitly from this. But then we sort of have an ambiguity of whether or not it's on this side of 1 or the other side of 1. So we have to figure that thing out. Okay, so we have this mapping. F of Z is equal to Z plus 1 over Z minus 1. And line we are considering the image of is L of C, which is this thing. It's the set of C plus IY for any Y belonging to this thing, right? And we've seen that f of the real numbers are the real numbers. And so if C is not equal to 1, then L of C is a circle, or f of L of C is a circle. Right? So let's draw a picture. So this is 1, and let's take C to be less than 1. Just put the line somewhere. This is L of C, and we are mapping it to a circle, and here, this is 0, because when we put infinity, then f of infinity is 1, so we are going through this, which is f of infinity, and we're also going through f of C, wherever that is, right? So just to put something, let's suppose f of C is here, and the circle we have does this. And because f of c is explicitly calculatable, we can find out the diameter of this circle and therefore the radius. So all we need to know is if the center is on the left or the right-hand side of 1. And actually, we can just consider this quantity. And then we have c plus 1 over c minus 1. And then minus, let's write this 1 as c minus 1 over c minus 1. And then we're going to have this cancellation. We're going to have this 2 over c minus 1, which is pretty convenient because then it says that if c is less than 1, then this quantity is negative, right? And therefore we are on the left-hand side, right? So of 1, so f of c is equal to 1 plus 2 over c minus 1. So we are to the left of 1 if c is less than 1, which is as this picture shows. And we are to the right of 1 if c is bigger than 1. All right. And the center of the circle is on the same side of 1 as f of c is, right? So this gives us the following good stuff. So we know that the diameter of the circle is, whether we're on the left or the right-hand side, the diameter of the circle is given by the absolute value of f of c minus 1, right? Which is just going to be 2 over the absolute value of c minus 1, whatever value of c is. Yeah? And the center of the circle is going to be half of this quantity, either plus or minus half of this quantity, depending on the sign, right? So, and the sign is actually encoded in the expression itself, right? So if c is less than 1, then we're on the left-hand side, and this is properly negative. So the center will be 1 plus 1 over c minus 1. Because if c is less than 1, then from this calculation, we know that f of c is to the left of 1, right? So we have to, and we know that we are moving by half of this quantity to the left of 1, which is exactly this, right? And if c is bigger than 1, then we are to the right of 1, right? So we are moving half of this thing, yeah? And if c is bigger than 1, it's still this expression. So the center, whether c is bigger or less than 1, is always this thing, yeah? So center and radius is exactly half of this thing, is 1 over, let's see, it's 1. So finally we can write that f of L of c is the fall of radius 1 over c minus 1, absolute value of 1 plus 1 over c minus 1 if c is not equal to 1. And this makes sense, right? Because, well, it makes sense because when we compare it to what happens when c is actually equal to 1, so if c is equal to 1, then this line goes through the 1, and therefore we are sending a line to a line. Then f of L of c is a line. It's a line that remains perpendicular to the real line, right? And it goes through 1. So line perpendicular and 1 belongs to L of. So that's pretty easy. Then it just has to be this thing, this line that goes like this. Right? Not a very good line. So what we see is that as c gets closer and closer to 1, this ball is tending closer and closer to this line, because as c gets closer and closer to 1, less than 1, then the radius is blowing up and the center of the circle is blowing up. So we are actually having a circle which has got center like way out here, and it looks more and more like this, right? So as c gets closer and closer to 1 from the left-hand side, then the image of this line is this larger and larger and larger circle whose center is more and more off towards minus infinity. Yeah, and if c is more and more close to negative infinity, then the circle is getting smaller and smaller and smaller in its radius, and it's getting closer and closer to 1. So circles with very, very big or very, very negative c are doing this. Right? And if c is bigger than 1, if it's close to positive infinity, again we have a circle which is kind of looking like this, where its center is way off like this. And if c is just a little bit bigger than 1, then we have, sorry, did I say this wrong around? I said this wrong around. Say this better. Say this correctly. So if c is just a little bit bigger than 1, but is bigger than 1, yeah, then this is a huge number, and so is this. So the radius is this huge radius with the center way out here, and looks more and more like the flat line, as we expect, because as c approaches 1, we expect it to converge to the shape we get when c is actually equal to 1, right? Or to the line or circle we get when c equals to 1. And when c is going towards positive infinity, then this is a very small number, so it's a circle almost centered around 1, just a little bit to the right of 1 with a very small diameter. So this is what it looks like. Right? So as c gets closer and closer to positive infinity, we get these smaller and smaller circles. And all of the circles, no matter what, always touch 1. So that is what this Mobius transformation does. And yeah, it turned out that we didn't need to use symmetry properties to figure out which way, which side of 1. We just needed to explicitly look at this. Another thing we could have done was just a case-by-case analysis of what happens to this expression as c is bigger than 1 or c is less than 1. Yet another thing we could have done is just take the derivative of this expression, because the derivative is either going to be positive or negative, because it's a Mobius transform, so it's invertible, and it's setting the real line to the real line. So it's setting the real line to the real line in an invertible way, which means that as we go from left to right, then the image has to go from, well, the image has to be either increasing or decreasing. We can hit infinity at a finite point as we do, but we are always either going to be increasing or decreasing, because we can't double back on ourselves, right? Because then it wouldn't be a one-to-one mapping. And sure enough, if we do calculate the derivative of this thing, then it's turns out to be, just differentiated top guy, leave everything on the bottom guy squared, x minus 1 squared differentiated top guy of 1. So we're just going to have 1 minus 1, so it's just going to be minus 2 like this, right? So it's the derivative is negative, so this function acting on the real numbers will be decreasing, and that too makes sense, right? Because as we have this vertical asymptote at 1, so we are at positive infinity just a bit bigger than 1. So we like try and graph this. Then if this is 1, then we're going down like this. Yeah, like this, with our decreasing function. And we have a vertical asymptote like this. Yeah. Yeah, and as x tends to minus infinity, this is going to tend more and more to 1. So, right, it's going to cross at minus 1, so it's going to be some sort of function like this. So this is what this function looks like on the real line. So it's a decreasing function for every x. Yeah, and yeah. So that's another way we can tell that for c which is bigger than 1, then f of c is bigger than 1. And for c which is less than 1,